So let's try to look at the partial derivatives. So what we want to try to do is um, to verify that this is in terms of mixed partials, by the way, that this is equals to that. Okay, so before we go into this question, it's very important that we understand what this means. Like, how are they different? Of course, they might appear like the same. It's more like they say these are they like when you're multiplying x and y. I can say xy is the same as y times x. These two are the same. Okay, it's more like you're saying 2 multiplied by 1, which is the same as 1 multiplied by 2. Okay, there's really no difference. But what are we saying the same thing? Are we also saying there's no difference when it comes to writing, when you're writing in terms of mixed partials? So let's try to check this out. So if let's say if we have we are differentiating, okay, we are finding the partial derivative with respect to, let's say, with respect to y of a function. Let's say in this case we have mixed partial of f with respect to what? With respect to x. So what this means is that at this point, okay, at this point right here, you had a function of f, okay, you had a function f, all right, you had a function f such as maybe you had, let's say, f of xy was equals to maybe say xy plus x squared plus 2y squared, like that. So you had to differentiate this function, or you have to find the partial derivative of this function with respect to x. Okay, so now you get whatever that you have, again you differentiate it with respect to y. That is what that means. And this can also be written as second partial of f, okay, with respect to y there, partial of y by partial of x, which is the same one that we write as fx y, like that. Okay, so what about another situation where we have that is the partial with respect to x. Okay, you had a function that you differentiated of, or let me say, whose you found the partial derivative of that function f with respect to y. Okay, so this can also be written as second partial of the function f with respect to x here. Okay, then with respect to y, like that. So meaning this is now equals to what? This will be equals to y by x. Okay, so this part here is what we have here. This part is what we have there. So in some like in this case, what we want to try to show is that for a given function that you have, this is equals to what? Is equals to that. These two are equals to each other. That's what we want to try to show. Okay, so now let's try to look at our first example. So let's say we are given a function f of x comma y, which is equals to x to the seventh um, ln of y plus sine x y. Okay, so first of all, what I would want to try to do is that I want to try to find my f of x. Okay, f of x, then x comma y, like that. So of this function, so meaning I'm finding the partial of that function with respect to x. So in this case, what I'm going to get is I'm going to get 7x to the sixth here. Okay, then ln of y, what is it going to be? This is going to be plus y cos xy. What have I done? I've differentiated this part with respect to x. I get y, which is this one. Then I differentiate everything that I have here, which is my sine xy. It gives me what? It gives me cos xy. Okay, so let me also differentiate in advance with respect to y. Okay, for this part. So I'll say my fy x comma y, it will be equals to, so we're differentiating this function with respect to x, I mean with respect to y. What are we going to get? So we are going to get x to the seventh divided by what? Divided by y. That is just ln of y. When you differentiate, you're going to get 1 over y, of which when you integrate you get back the ln of y there. Okay, so this is going to be plus x uh, cos xy. Okay, there's not much of a difference, just that when you differentiate this part, you find the partial derivative of that part with respect to y. You're going to get x, which is the x that I've placed at that point. Okay, so what follows is that I have to differentiate this now with respect to what? With respect to y. So that would be fxy of x comma y. What is it going to be? So I'll differentiate this part. I'll find the partial with respect to y, of which we leave x the 7 and the x the power 6 as a constant. What you're going to have is something like 7x to the power 6 divide by y. Okay, then this is going to be minus, that will be, I believe that will be minus. So you differentiate this with respect to what? With respect to y. What you observe is that, oh, in fact, let me not put a minus just now, let's say a plus. So this is a product of two functions. Why am I saying so? If I had x here, I could have maintained my thought to say it's one function, in the sense that I'm differentiating, or I'm finding the partial derivative with respect to y. I mean, with respect to x rather. So if I was finding the partial derivative of this with respect to y, but here I have x, I'll just take it just as a single function. But because I'm finding the partial derivative with respect to y, and I have y here, meaning those are two functions that are multiplying each other. What am I going to do? I'm going to say y, then I'll differentiate this part. What am I going to have? I'm going to have minus, differentiate this again with respect to y. You're going to have y sine xy, then we say plus, that will be derivative of that is what is 1, so you're going to get cos xy. Okay, you're going to get cos xy there. And by the way, it appears I'm supposed to use x here. Yeah, so this is supposed to be the derivative of this part with respect to y. You're going to get x, so that would be sine xy. Okay, then we say plus, uh, plus what? Plus cos x y, like that. So what you end up getting is that you're going to get 7x to the power 6 divided by y. I'll say plus cos xy minus xy sine xy, like that. That's what I get. Okay, so now we'll try to compare what we have here with what you're going to look for on the other side. Okay, that's what we get. So let's try to now determine the our f y x, okay, of what we have right there. So you're going to try to differentiate this now with respect to what? With respect to x. What you're going to get is that you're going to get 7x to the power 6 divided by y. You just drop the 7, reduce it by 1. So here again it's a product of two functions, because I'm differentiating with respect to x. That would be plus, I differentiate this part, I maintain the x, that would be like minus x. Differentiate this part with respect to s, you get what? You get y, then that would be sine x. Then I'll say plus what? Cos xy, because I maintained this one, differentiated that one, that it just gave me a 1. Okay, so now what do we end up having? What we end up having is 7x to the power 6 divided by y. That would be plus cos xy minus xy sine xy. So what we have here and what we have here are the same, hence we have done what? We have verified. Okay, let's try to look at another example, just to make sure to say we are familiar. We familiarize ourselves with how we deal with such questions. So let's say we are given something like f of x y is equals to 3x squared y minus 2xy plus 5y squared. Okay, so once again, first things first, we find our f x y, I mean x comma y there. That will be equals to, I'll differentiate, I'll find the derivative with respect to x, but meaning I'm going to treat my y as a constant. So what this is going to be is that I'm going to have a 6x to the power 6x times y. Okay, then minus, that will be 2y. This is a constant, to just be 0. So if I say fy x comma y, what is it going to give me? I'm going to get 3x squared, okay, for this part, because differentiate y, that would be a 1 by 3x squared is 3x squared. So minus this part, you're going to remain with a 2x, okay, plus drop the power there, it will be 5 times 2, giving us 10 y, like that. So now I have to find my fx y of that function. So what is it going to be? We are differentiating this function now with respect to what? With respect to y. So what I get is simply 6x minus 2, I come to this one, fyx. How is it going to be? This is going to be 6x. Yeah, 6x. We are differentiating with respect to x. Then this will be a constant. It will be a 0. So we get a 2 there. We observe that this part is equals to that part, which is very, very simple for this question. Let's try to look at another example. Let's say we have f of x comma y to be equals to um, let me say e to the x cos y. Once again, I like taking these simultaneously. So let me say f of x comma y like that. How is it going to be? I differentiate with respect to x. Just get the same thing. Why? It's uh, because that's the way it is. But how is it like that? You This part is the one that has an x term. So what do? That's an exponential. I just multiply to differentiate. I just multiply by the derivative of the power. In this case, that's just x. So the derivative of x is 1. So I just like had to multiply by 1, but I don't need to indicate it the one. I don't need to indicate the one anyways. So fy x comma y, what is it equals to? So we differentiate that with respect to y. What you're going to get is minus e to the x sine y. The derivative, of course, is simply minus sign. That's why you have a minus there. So your fxy x comma y, that will be equals to, now differentiate with respect to y. Differentiate that with respect to y is going to be minus e to the x sine y. How? You differentiate that, you get minus sign. That's what we have right there. So now I'm going to find out fyx x comma y. What is it going to be? Now we differentiate this with respect to x, which is still a 1, so that we're still going to get minus e to the x sine y, of which this and that are equals to each other. Hence, we have verified. Okay, so there are a lot of questions that we can do regarding these mixed partials, but that will be our last example for that part. What I'd want to try I would love to look at a question on that has to do with Laplace's equation. Okay, so how I pronounce and how you pronounce depends on where you're coming from. Okay, yeah, that, which is simply equals to fxx plus our fyy is equals to 0. So now remember, like, when, let's say if you have your fx comma y to be equals to, let's say, xy xy squared plus 2xy. So if I find my fx, okay, the derivative, meaning the partial derivative of that with respect to x, you're going to get y squared plus 2y. Then again, if I come and say fxx, what am I looking for? Like, what am I looking for here? Like, you're differentiating this function again with respect to x for the second time, of which you're going to get a 0. So that is what it means. So it's like I can even find my f of x there, another of x there. So meaning I keep on differentiating the function. I keep on finding the partial derivative of that function with respect to x. And yeah, that's simply how you go about that one. So what we have to do is that we have to verify that that and that is equals to 0. That is for a function that we are given. Okay, so now let's say we have this function. Let me put this aside. Okay, so this is fx comma y. We say it's equals to, let's say it's equals to ln of x squared plus y squared, like that. Okay, so what I would do is that first of all I have to find my first my f of x there. What is it going to be? Uh, so this is simply going to be I'm going to say 1 over x squared plus y squared. I'll multiply by the derivative of that, but of course that is in respect to what? To x. That will be what? That will be 2x. And I don't need to put it here. I can put it on the numerator here. That's going to be 2x divided by x squared plus y squared. I'll do the same. Let me say my fy is going to be 2y divided by x squared plus y squared. So what I'm simply doing here is that I'm dividing by what I have right here, but again multiplying by the derivative of what you have there inside the brackets with respect to, in this case, x, in that case y. Okay, that's simply, you just have to remember how we differentiate uh, natural logs. Okay, so I have to differentiate for the second time here. Okay, so I have to find what my second derivative is for that one with respect to x. So now it's up to you which method you want to you want to use. um for me, I think I would love to use the quotient rule. Yeah, so in this case I'll say my u is equals to 2x, meaning my u prime will be equals to, wait a minute, now this is where it gets interesting. Like, you ask yourself, are you differentiating with respect to x or with respect to y? In this case, I'm differentiating with respect to x, so meaning I'm going to get a 2 here. If I was differentiating with respect to y, it's obvious I was going to get a 0. Yeah. So now, for v, which is our denominator, which is x to the second plus y to the second, v prime, in this case again, I just said v prime, I just didn't say vx or ux in terms of u. But I just have to remember, okay, I'm differentiating with respect to x, so meaning this is a constant, I get a 0, so this is going to be 2x. Okay, so now, meaning my second derivative of that function, or let me say my second partial derivative of that first partial derivative, will be equals to u prime multiplied by v, which is going to be 2x squared plus 2y squared, okay, minus what are we going to get? Minus u by v prime, which is going to be 4x squared, divide by v squared, which is simply x squared plus y squared, like that. What we get? Okay, let me try to write it right here. So f, the second derivative, partial derivative there. So we get, we're going to get 2y. I'm trying to use a different color. So we're going to get 2y squared, which is this part, minus 2x squared, divide by our x squared plus y squared squared, like that. That's our v. Okay, so for this one, our y there, what will happen is that if you use the same method, the quotient, we are going to arrive at 2x squared minus 2y squared, divide by uh, x squared plus y squared squared, like that. Okay, so now we have to add these two, okay, which is this one and that one, which translates to this one and that one, and we just have to bring them together. That would be like 2y squared minus 2x squared, divide by x squared plus y squared squared, plus 2x squared minus 2y squared, divide by x squared plus y squared squared. Want to see what that is equals to. Okay, I'm not saying that to be equals to 0, but we just have to verify it to say it's equals to 0, because that's what we have. That's what we wanted to do in the first place anyway. So the common denominator, that is what we have here. So this is going to be x squared, or maybe I don't even have to do that, since wait, am I allowed to say these are the same? Maybe not. Let me take it step by step. That would be x squared plus y squared squared. Okay, on the numerator you have your 2y squared minus 2x squared plus 2x squared minus 2y squared, of which this and that goes, that and that goes. You have your 0 divided by your v squared, which is going to be what? A 0. So you have verified. We have verified. Yeah, we have verified together. Okay, let's try to look at another example. All right. So so let's say we are given our function f of xy f of xy is equals to uh, tan inverse of x, no, not x, but y over x. Okay, so now what to happen is that as we find our, remember to say we have to find our first derivative with respect to x, first partial derivative with respect to x. How this is going to be is that you're going to get the derivative of this one, okay, multiply by the derivative of that with respect to x. We have done a lot of videos on how to differentiate um, inverse trig functions, and I'm not going to go through that those steps. Okay, I'm not going to go through those steps. So when you differentiate this, what you're going to end up having is you're going to end up with x squared divided by x squared plus y squared. That's the derivative of everything here, okay, but we're going to multiply by the derivative of what you have inside here with respect to x. Okay, so in this case it's more like you have your y, x to the negative 1, you differentiate that, that will give you minus y over x squared. So this will be minus y over x squared like that. So what you observe is that this and that goes, okay, so what do we remain with? What we remain with is minus y over x squared plus y squared. So following the same steps, okay, you'll find that your f of y here of that function, meaning the partial derivative of that function with respect to y, is going to be equals to x over x squared plus y squared. Alright, so now I'm going to skip a step here, okay. Say this was equals to minus y over x squared plus y squared like that. So I'm going to skip a step since we just follow the same steps that we used in the previous example. You either use the chain rule or the quotient rule. So my f of x, or the second partial derivative of that, that will be equals to 2xy divided by x squared plus y squared squared like that. That was our v if you had to use your quotient rule. So that is going to be your second partial derivative of y with respect to y. Okay, so what are you going to get? You're going to get something like minus 2x y divided by x squared plus y squared squared like that. So what do we get? We have to add these two. So you observe to say if you say 2xy divided by x squared plus y squared squared, that would be plus, but I'm going to say minus because of the minus that I have there, which is 2xy divided by x squared plus y squared. You have your squared there. What is this equals to? These two are the same and they're subtracting each other. What we end up having is a what? Is a 0. Hence we have what? We have verified. Okay, and that's simply how we go about answering those questions. It's just a matter of us remembering how we differentiate. More especially there are such questions uh, they appear a lot, so it's very important that we remind ourselves of um, how we differentiate inverse trig functions. Okay, so that's all in this video. Thank you very much for watching.